Comparative analysis of order roll-off of filter and imperative study of step response of filter using Xilinx IP core. Abstract signal separation and signal restoration are two of the most commonly used phrases in digital signal processing. Filtering is an essential part of both their workflows. For removal of undesired components from a signal, a filter is a useful tool in signal processing. Due to their greater adaptability than analog counterparts, digital filters have becoming increasingly popular and preferred one. In this paper, we'll discuss a low-pass FIR filter constructed in Matlab and its implementation in Xilinx Nexys for FPGA. Paper also demonstrated implementation of different FIR filter parameters and investigates with filter builder tool. Finally, the paper presents the FIR filter IP core in Vivado platform and Verilog to build the FIR filter designed in Matlab on Xilinx Nexys for FPGA. Introduction. Using Matlab to design the FIR filter simplifies the intricate computations involved in simulation and improves performance. Matlab processes the design of FIR filter utilizing window function, frequency sampling, and convex optimization techniques. The amplitude frequency characterization can be accomplished with the help of Matlab-designed application. By comparing the signal's amplitude frequency graphs created by the FIR digital filters used to process the input signal with the Matlab function, the filtering effect of various digital filters is studied. A digital filter is a discrete system that can perform a series of mathematical operations on the input signal in order to extract the needed information from it. The transfer function for a time-invariant linear system. The experimental results demonstrate the effectiveness of the FIR filters described in their study. 2. FIR filter. FIR is an abbreviation for finite impulse response. A FIR filter is the one that has finite period impulse response. The impulse response of a nth order FIR filter is n+1 before it settles to 0. Precisely. A FIR filter is a filter whose impulse response settles to a 0 over a specified time period, hence making the response finite. The time required for the impulse response to reach 0 is proportional to the order of filter. FIR filter is capable of matching phase and amplitude requirements. It also eliminates draft and noise. The underlying premise of the FIR filter is as follows: the impulse response of a FIR filter h, n, for a series of length n, in addition to meeting phase and amplitude requirements, this filter eliminates drift and noise. The FIR filter's fundamental premise is as follows: the transfer function of a FIR filter's impulse response h, n, for a series of length n. And the differential equation for the same is 3. FIR filter design. The window approach, such as the Kaiser window method, is used to create FIR filters. To construct FIR filters using the window technique, the fundamental principle is to calculate HD, n, using the anti-Fourier transform based on the ideal desired filter frequency response. HD, EDGE. As the formula for HD, n, is infinitely long, to get the unit impulse response h, n, we have to use the window function to meet the requirement. The W, n, is the window function in this case. Filters are the devices that allow only some signals to pass through while rejecting the rest. It is necessary to apply the same idea to LIA, lock-in amplifier, which is why the use of a filter is essential. For design of FIR filter. The overall methodology of experimentation is demonstrated in the following figure. Fig 1.1 block diagram of the experiment. The magnitude characteristic of the frequency response is determined by FIR filter with a polynomial transfer function in the z-axis and zeros in the z-plane. FIR filters produce a phase response that is perfectly linear. A non-recursive strategy is used to construct the FIR filter, which results in a stable filter. Two sections comprise the FIR filter design. 1. An preliminary analysis of the given problem. 2. In-depth analysis of the problem. 3. In the analysis step, we take the specified object and generate a transfer function. The next step to specify the transfer function. An optimal response is chosen, which is often in the frequency domain. 2. For FIR filters, the length m is chosen. 3. A criterion for the analysis's quality is chosen. 4. To determine the optimal filter transfer function, a flowchart is used. mmm.png. Fig 1.2 Specification of Lpf Filter. As illustrated above, the transition band is always located between the passband and the stop band of filter. The passband frequency S determines the stop band frequency P, and the passband frequency P marks the passband H. Thus, transition band's width is determined by the difference between .S and .P, ds ripple or attenuation in the stop band. The ripple or attenuation in the passband of the filter is denoted as dP, and the magnitude of the filter varies from dp to dp. The ripple in the pass band is 20 log 10 dp dB, and the ripple in the stop band is 20 log 10 ds dB. Matlab provided FPGA tool automatic set the ripple at cutoff frequencies fixed at 6 dB, half of passband gain. V-window function. In many cases of stable FIR filter, most selective approach to obtain a causal finite impulse response is to truncate it or smoothen the ideal unit response. We start with fixed, desirable, frequency response in filter specification HD, E⁻JW, and determine unit sample response, N, hence HD, N, is correlated to HD, E⁻JW, by Fourier transform relation. Some example of window function can be used practically. 1. Triangular window. 2. Hahn window. 3. Hamming window. 4. Kaiser window. In our project we use Kaiser window function because we want stable filter. We understand window function method very well with the help of Matlab FPGA tool. Below is the graph of order of filter vs cutoff frequency. Here, the less the difference between pass and stop, the order of filter will be high, and vice versa. This graph is obtained by using the filter function from Matlab. One can obtain a similar graph, for that keep the pass value constant, and then vary the stop. In our case, we have varied the stop from value 900 to 1000 Hz. By varying these values we observed that the difference between pass and stop started increasing, and so the value of order of filter started dropping down. Below is the graph of order of filter vs settling time. Settle time vs order.jpg. The above graph is obtained by using the filter function from Matlab. One can obtain a similar graph, for that keep the pass value constant and vary stop. In our case we have varied the stop from value 10 to 100 Hz. By varying these value we observed that difference between stop and pass, so the value of order of filter start decreasing, and we obtain settling time using step impulse function. We analysis that for maximum order of filter value maximum settling time. 6. Kaiser window. Kaiser window parameter are affecting the side lobe and attenuation of Fourier transform of the window. In our case its value by default for beta is 0.5. To verify a Kaiser window design in FIR filter with side lobe attenuation of a dB, use following SS syntax in Matlab: y equals Kaiser, KSS. Where y equals Kaiser, KSS, return and k-point Kaiser window in the column vector y, and SS is Kaiser window parameter. Example: y equals Kaiser, 500, 0.5. Here, we can observe that for certain parameter we obtain 1025 order, which is more essential for stable filter design. We also observed the behavior of roll-off vs cutoff of a low-pass FIR filter. The graph above is the final result. Here, roll-off is the steepness observed in a transfer function with certain frequency value. The graph was obtained on Matlab's filter function, where the value of cutoff frequency was decreased. By doing so it was observed that the slope or the roll-off started becoming steeper. Here's the roll-off gets steeper as the values of pass and stop are close to each other. On the other hand, as the difference between pass and stop is small, the roll-off isn't steep. For a gradually changing roll-off the result will be a lower floater order. 7. Nexys 4 board. Arctic 7 FPGA DDA board. The Nexys 4 board is a complete development platform based on the latest Arctic 7 FPGA. The Nexys 4 board is compatible with Xilinx's optimized for high-performance logic, and offers more capacity, higher performance, and more resources than earlier designs. In this project we required 15,879 logical DSP slices, each having 6 LUTs and 8 flip-flop. Also RAM is required 4,800 kbits, and 240 DSP slices is used for reduced DSP utilization. 8. FPGA implementation. For trying out the FIR filter built in the Filter Designer tool of Matlab, we created a coefficient file from Matlab and imported it into the FIR IP core in Xilinx Vivado. After interesting the coefficients file, we integrated the IP into our Verilog code. We also used integrated logic analyzer IP of Xilinx to observe the simulation results of our code. The code is written in Verilog HDL. 9. Future scope. Digital filters give us advantages when compared to analog filters, in terms of reprogrammability and repeatability. Also, the digital filters are less sensitive to environmental changes, noises and disturbances. These features of digital filter can be used in several applications. Further, we will be use this optimum filter design in digital lock-in amplifier on an FPGA board. Conclusion. 1. FIR filter design generally consists of 2 sections. 2. Analysis of problem. 3. Realization problem with deep approach. 4. Basically, there are 3 approaches for filter design. 5. Function window approach. 6. Frequency sampling technique. 7. Optimal filter design approach. 8. The major advantages of using window method is their relative simplicity as compared to other methods and ease of use.